Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are at lecture 18 today and we are discussing today, in the last lecture we discussed about the surface forces and interfacial forces, interfacial energies, and I introduced the idea of Van der Waals force of interaction, and I presented that I showed that the interaction energy between two parallel flat surfaces goes as u is equal to minus A12, that is the Hamaker constant, by 12 pi d square. D is the distance between these two parallel flat surfaces, and the interaction energy between the particle and the surface can be represented by this equation, u is equal to minus A r by 6 d, and that between two spheres of radii r1 and r2, which is r1 and r2 much larger than d, and the gap between them, the distance between them, can be represented by u is equal to minus A, that is the Hamaker constant, by 6 d r1 r2 by r1 plus r2. And I also described about the Hamaker constant, how it is related to different parameters, and I did not present the detailed calculation that how A12 is calculated, but you can find it out from literature. So today I am going to discuss about, continue the discussion, and I will show that how to estimate the interfacial energies, which is very important for our adhesion studies. So we will talk about solid liquid interfacial energy, surface energy of a liquid, and so on. So here we have, let us say, these two materials, same material, let us say, and therefore represented by 1 and 1, 1 and 1. They are at a gap L between them, medium is vacuum. So the Hamaker constant is A11, and the interaction energy, free energy of interaction between two surfaces can be represented by F11 is equal to minus A11 by 12 pi L square. So that is the interaction energy between these two surfaces. Now let us say that initially these two surfaces are at a distance infinity apart, and now they are being brought closer. So when they are in infinity, the initial state, the interaction energy between them is 0, and now they are being brought closer and closer, and at an infinitesimally small distance L0. So remember that in the last lecture I talked about the repulsion, okay, that happens when the bodies come very close to each other, that is called the bond repulsion, and the distance between them, the equilibrium distance that is reached eventually, okay, I said that is about L0 or R0, that is what I had written in the last lecture. So that is the L0, let us say. So when these two materials are brought close enough, that is L0, so that is very small, so almost these two materials have come closer, okay. So that is what we will say, that when the distance has reached L0, that means that is that equilibrium distance. So these two materials have been almost bonded together, so that is basically the cohesion of these two materials, okay. So it is the same material 1 and 1, let us say two different water drop which are being brought closer and closer and closer, and when it reaches L0, okay, which is infinitesimally small. So when these two drops of water, let us say they coalesce, so they form one single drop, and that is actually the cohesion of these two materials. So you can see the change in the free energy in this process is 0 at the infinity, and then this quantity at when it is very close. So it will be given as minus A11 by 12 pi L0 square, okay. Now what this quantity means in terms of practical terms, because practically we do not measure L0, and Hamaker constant I had given a very that is a very involved relation. So practically what it matters for us is something like this. Let us say that two materials are separated in vacuum, and so these two surface, every surface has some amount of energy, okay, this is called surface energy. So energy associated with this surface. So this surface has energy, let us say gamma 1, and this surface also has energy gamma 1, and when these two surfaces are brought together, then since they are the same material, there is no surface between them, the surface between them goes, because they have now, there is a cohesion that has happened. So these two materials have come closer together, so this is cohesion here. So as a result there is no interface there, okay. Since there is no interface, so there is no energy, interfacial energy there, okay. So, as a result, the change in free energy for this case, when the same materials are brought together or cohesion of the same materials, the final state there is no energy there, interfacial energy, that is 0. Initial energies are gamma 1 and gamma 1, so that is minus 2 gamma 1. So, the change in free energy because of the cohesion of this material will be minus 2 gamma 1, and minus 2 gamma delta F11 in the last slide I have derived it as this is equal to minus A11 and 12 pi L0 square. So, since these two quantities are equal, so therefore, this gamma 11 can be written as A11 divided by 24 pi L0 square. So, surface energy, this is the energy that is per unit area. Okay. So, that is what we define this Hamakar constant. Okay, the way it is defined, it would also be energy per unit area. Okay. And so, therefore, Hamakar constant is unit will be joule, and since it is divided by L0 square, the delta F1 will be energy per unit area. So, here this gamma 1 is the energy per unit area, joule per meter square or millijoule per meter square, that is the way it is expressed, and this gamma 1 is the quantity that we normally deal with or measure or estimate. So, we will come to that, and but then the idea of gamma 1 comes from this idea that Hamakar constant is there and same material, these are brought together from infinity, cohesion occurs, and similarly when these two materials, when a material is broken into two pieces, let us say this from we go from this side from a same single material, we break into two materials. So, two surfaces are created. So, equivalent amount of energy has to be given. So, if you say ask how much amount of energy is required to break a material into two pieces, then one has to thermodynamically, this is a thermodynamic quantity. So, thermodynamically amount of energy that will be required is associated with the amount of surface that is being formed, and for per unit area that the surface is formed, it will be gamma 1 amount of energy. So, two surfaces, so 2 gamma 1 will be the amount of energy that will be required for per unit area of the new surface that is created. So, that is the way it goes. So, surface free energy per unit area of a liquid or solid is essentially the half of the free energy change due to cohesion of the material in vacuum. So, that is what is the idea here. Now, that was same material 1 1, but let us say we have got two different material. Now, consider two different materials. So, you have got now 1 2, and when you have 1 2, then of course, we need to then estimate the interfacial properties, interfacial energy between these two materials, let us say gamma 1 2, and this 1 2 can be liquid liquid, two different liquids, two different solids, or two different or a liquid and solid, okay, or all these things can be. And so, we need to estimate this gamma 1 2 because that is what will determine that when two materials come closer, when they will attract each other, when they repel each other and all that. So, we have this particular problem at hand, how to estimate the interaction energy, interfacial energy between two different materials. Essentially, we are talking about this particular quantity gamma 1 2. So, this idea comes from actually from the ideal gas to real gas, okay, that idea. So, I will just describe it and how it is determined we will describe. So, now let us say in ideal gas there is no interaction between molecules, we know that, and therefore, in the equation of state for let us say single mole of the ideal gas will be given as PV is equal to RT, that is very simple. However, you also know that when there is a real gas there are interaction between the molecules. So, therefore, the actual volume of the that needs to be considered is not V, but V minus B. So, the B size accounts for the finite size of the molecules, this B quantity here. So, that is V minus B, and P plus A by V square in the sense that A accounts for the interaction, okay, between the molecules. So, the molecules, it is not that the molecules are not interacting, molecules do interact with each other, and so the account of strength of the intermolecular interaction, that is accounted by this quantity A here. So, this quantity P plus A by V square, that accounts for that actual pressure, okay, within the effective pressure that acts within the material, within that particular gas. So, this A accounts for that. So, that becomes the consider. So, now this is for let us say single molecule or single species present, but in a mixture of gases when there are several different species, then this A and the B has to be determined for that mixture of gases, because within the mixture of gases, the molecules of A that collides not only with molecules of A, molecules of A and 1 does not collide with molecules of 2, molecules of 3, like that. So, it is there are 2 different species, 1 and 2. Okay. So, therefore, the A, that is the strength of intermolecular interaction, that has to be accounted for, and that is done by considering this particular kind of mixing rule. And the mixing rule that works is something like this: square root of A11 into A22. So, A11 considers or accounts for the interaction between the molecules within species 1, I mean the 1 and 1 interaction. A22 will account for interaction between molecule within molecules 2 and 2 interaction. But square root of A1 to A11 and A22, that accounts for the interaction, the combined interaction basically. So, this is the mixing rule that is used, and this quantity B12, that is also determined by this kind of formula. Remember that these formulas are more or less empirical, okay, but it works. There might be quantum calculations and all that, that also possibly statistical calculations that can also give rise to similar equation, but for our purposes we will not worry about how we get this equation, but we will accept it, okay, like that. So, we have this mixing rule over here, and this kind of mixing rule is used when you consider this attractive constants between molecules, like the Hamakar constants between these 2 different molecules, say 1 and 2, and capital A11 and capital A22, these are the Hamakar constants. And so, the interaction Hamakar constant of interaction between the unlike molecules will be given by A12, and that is given by A12 is equal to square root of A11 and into A22. So, that is the way it is actually obtained. And since that is the way this kind of mixing rule used for Hamakar constants, for determining the interaction energy or free energy of adhesion or interaction between 2 different materials are also determined by this. So, here delta F11 will be the free energy of cohesion between molecules of 1, free energy of cohesion of between molecules of 2, that is delta F22, and so therefore, the free energy of interaction between these molecules F1 and 2 is given by like this, using this kind of mixing rule. So, that is the way it is done. So, now we know that we have derived it earlier that delta F11 will be given by this 2 gamma 1 LW. So, LW means this is a Lipschitz van der Waals component. Okay. Now, why I am writing LW here, that will come, that will be clear after some time, that why I am writing LW, but for the time being let us accept it that this is the LW Lipschitz van der Waals component of the interaction, that basically the dispersion interaction, okay, that is the London force. So, that comes out to be F11 delta F1 is equal to 2 gamma 1 LW, delta F22 is 2 gamma 2 LW, and so therefore, from this mixing rule what I have is that you multiply that. So, you will get delta F12 is equal to 2 gamma 11 LW 2 into gamma 2 LW, like that. So, now what is happening is something like this. Suppose you have got, let us say this is material 1 and let us say this is material 2, okay, and now let us say they are coming closer. So, let us say we have got this material after bonding or adhesion or something like that, they are something like this. So, now this has the surface energy of gamma 11, this has the surface energy of gamma 22, there is a this, when they combine together the interfacial energy is gamma 12. So, the change in the interfacial energy delta of 12, that will be what? The final energy is gamma 12 minus gamma 11 minus gamma 22, in each case I will write LW because that is the component that I am discussing about, and I will come to that. I have said that why LW, I will come to that in a minute. So, like that. So, this is change in the, so I think there is a problem with my plus or minus, that does not matter much, let us say this is okay. So, here this will be the change in the interfacial energy, and since gamma 12, okay, I will write it as, therefore, okay, now so delta F12 that will be written as, this quantity is written as 2 square root of gamma 11 LW into gamma 22 LW, and so therefore, this gamma 12 is written as, so there is a minus sign will be there from here, there is a minus sign. So, therefore, this gamma 1 2 is what we have derived over here, it comes out like that. So, gamma 1 2 LW, that is the interfacial energy, will come out to be gamma 1 LW plus gamma 2 LW minus 2 square root of gamma 1 W gamma 2 LW. So, this comes directly from this. So, let us do some small problem here. Let us say there is a drop of water that is dispensed on a rubber surface, silicon rubber or like natural rubber or something like that. So, now let us say that the LW component of water is 21.8 millijoule per meter square, and let us say there is another liquid, this is pentadecane here. So, pentadecane has LW component 27.1 millijoule per meter square. This rubber has got a LW of 22.1 millijoule per meter square. So, let us try to find out that what will be this LW component of the interface between water and rubber. So, as it is given, this is gamma 1 LW, so that is let us say 21.8 plus rubber, so that is 22.1 minus 2 into square root of 21.8 into 22.1, this many millijoule per meter square. So, we have to find out, calculate it, and over here this quantity will be, let us say this is pentadecane. So, pentadecane has LW 27.1 plus this is 22.1, sorry 22.1 minus 2 into square root of this is 27.1 into 22.1 millijoule per meter square. I hope I did right. Yeah, so like that. So, now you can find it out. Now, so we can find out the interfacial this component, this particular component LW component, let us say, of the interface like this. So, we can get some idea of that what will be the interfacial energy by this kind of calculation. So, we can find it out. Now, this equation which we have derived here, the delta F 1 to LW, okay, so that is the final energy, interfacial energy minus initial energies. So, this equation and this is done in vacuum. Okay. So, this 1 and 2 they are interacting with the vacuum over here, that means air, let us say. This is called the Dupré equation, and so this is also we have just derived. So, this is fine. Now, let us say that what is the delta F LW, that means the interaction energy between 1 and 2. So, that also we can get, and that will be given as this is minus 2 and this is square root of gamma 1 LW, let us say 21.8 into 22.1 millijoule per meter square, millijoule per meter square. So, you can find out what is that. Here minus 2, here it is 20 instead of pentadecane is 27.1 into, let us say this is 22.1, right. So, we can find it out that what will be the delta F, that is the interaction energy between those two materials, water and rubber here, and pentadecane and rubber, we can find it out. So, this is the way. So, just to demonstrate the kind of calculation that we can do. So, this quantity comes out to be minus 44 here, this comes out to be minus 49 millijoule per meter square. Now, let us say that there is a medium 2 between this material 1 and material 2. So far we are discussing about vacuum, but now let us say we have got in between this material. So, delta F LW 1 to 1, okay. So, 1 this surface 2 and this surface 1. So, there are two interfaces 1 2 over here, there is no interface because 1 and 1 they are being joined together. So, for example, if you ask me for an example, so example can be, let us say in water you have put 2 drops of oil, okay, and there is no stabilizer, emulsion stabilizer, then you will see that the oil phase they try to come closer and come and then form a single phase. So, there the same thing happens. So, now what is the change in the interaction energy when that happens? Again over here you can see that there is when they are bonded together. So, there is no energy, there are no interface there. So, this is 0 here, and then minus gamma 1 2 let us say LW and minus gamma 1 2 LW like that. And so, here it is might be minus 2 gamma 1 2 LW because there is no 0 here because there is no interface as I said. So, this interaction energy between molecules of particles of material 1 immersion in material 2 liquid 2 that will be considered, that will be something like this. Now, let us say that there are two different materials which are placed inside the medium 3 here. So, there is two interface here, gamma 1 3. So, this is medium 3, gamma 1 3 here, and let us say this is gamma 2 3 here, it should be 2 here, right, 2 3 here, gamma 2 3 here, and there is an interface here. So, this interface is gamma 1 2. So, the energy of interaction between two different materials 1 and 2 and immersed in a medium of liquid 3, that we need to find out. And here again, so it will be delta F, and we are writing is 1, let us say 2 3 1 3 2 or like that, LW, 3 is in between. So, here let us see there is an interface that is formed. So, that interfacial energy is 1 2 minus this is gamma 1 3 and minus gamma 2 3 like that. So, this will be the interaction energy between them, just like that. So, now what can I do with this? So, gamma 1 2 LW, that can be expanded as gamma 1 LW plus gamma 2 LW minus 2 square root of gamma 1 LW into gamma 2 LW. Like that I have, let us say, gamma 1 3, gamma 1 3, gamma 2 3, gamma 1 2, gamma 1 3. So, gamma 1 3 will be gamma 1 LW plus gamma 3 LW minus 2 square root of gamma 1 LW, gamma, this is 3 here, LW, gamma 2 3 will be gamma 1, sorry, gamma 2 LW plus gamma 3 LW minus 2 square root of gamma 2 LW and gamma 3 LW, like that. And let us put all together into this formula. So, delta F 1 2 3 1 3 2 LW. So, delta F 1 3 2 LW. So, that will be given as gamma 1 2 LW. So, gamma 1 2 is gamma 1 plus gamma 2 LW minus 2 square root of gamma 1 LW into gamma 2 LW minus gamma 1 LW minus gamma 3 LW minus minus plus here 2 square root of gamma 1 LW, gamma 3 LW, and then minus minus again minus here. So, it is gamma 2 LW minus gamma 3 LW plus 2 square root of gamma 2 LW into gamma 3 LW. So, if you add up all that, so you will see this one gets cancelled here, this one gets cancelled here, and then the whatever is rest, I can write something like this. You please check if I am writing correct or not. This is gamma 3 LW minus square root of gamma 1 LW into square root of gamma 3 LW and minus square root of gamma 2 LW. I guess I need to have gamma, so this is minus minus plus here, plus is fine, is plus minus here is fine. So, 2 here I guess I need. So, here it will be delta F 132 LW, like that. So, I have this equation, right, and so this equation. So, now we have this. Now, this is the relation, now the interaction energy between materials 1 and 2 in medium 3. Now, when there will be attraction, I said when the attraction happens, then the energy decreases. Remember that when the attraction will happen, only when the energy decreases, because that is a spontaneous process. So, two materials spontaneously they will attract each other when the interaction energy decreases. So, it decreases, become negative here. So, the attraction will become this delta F 132 LW, that will be negative over here. So, when that will be negative, where will be when the square root of this gamma 1 3 LW. So, rather gamma I can 3 just LW is greater than gamma 1 LW and gamma 3 LW is greater than gamma 2 LW, right. Or let us say when gamma 3 LW decreases smaller than gamma LW and gamma 3 LW is smaller than gamma 2 LW, like that. So, when either of this condition or this condition gets satisfied, then we have this term, whole thing will be delta F 132, that will be negative, and then there will be attraction for between these materials. And yeah, so what it means is that gamma 3 will be greater than both gamma 1 and gamma 2, and gamma 3 can be get less than gamma 1 and gamma 2 both there. So now there is an example here for some paper here by these authors. Now here let us say there is a medium water and then there are silica particles, these are SiO2 microparticles, okay, and these particles are actually spread, these are microparticles, colloidal particles. So they show Brownian motion, they are not affected by gravity or density difference or anything. So they just fluctuate or roam around within the liquid, and now there is a drop of or a pool of, this is called silicone oil, this is a silicone oil, okay, silicone placed in between. So now what happens? What happens is something interesting. These particles, okay, they now tend to migrate on the surface of this silicone oil, and that happens because of this reason, that can be explained by this interaction energies and by this surface energies. For example, over here this gamma 1, okay, Lw, so gamma 1 is basically silicone, so the silicone has the energy of 23.42 millijoule per meter square. Gamma 2 is the silica particle, so silica particles has whatever is the surface situation, surface condition, let us say it has the surface energy of 26 millijoule per meter square, and gamma 3, that is water, 3 is water here, so 21.8. So in essence it is something like this, this is let us say silicone oil, and let us say this is the microparticle, this is silica particle SiO2, and in between you have got water here like that. So since this gamma 1 Lw, that is 23.42, that is larger than this, and gamma 2 Lw, that is 26. So 26 is silica particle, that is also larger than 21.8, that is gamma 3 Lw. So these microparticles feel attracted by this silicon drop and they migrate to this silicon placed inside water, and consequently migrate, and not only, you just see, they not only migrate but they go inside, deep inside, that means silicone oil can actually wet the surface and there is an equilibrium, okay, angle, contact angle that forms. So we will come to that equilibrium contact angle a little later, but that is how it happens. So today I will stop here and I will take up this calculation of interfacial energy again in the next lecture. Thank you for your kind attention.